Hi everyone, welcome back. So in this video, we are going to look at some of the structured questions for the 2023 Science Physics paper. So let's start with question 1 of section A. So a girl sits on a swing and is at rest, so she's given a big push, and this time for the girl to swing from her original rest position to the maximum point is 1.17 seconds. So in part A, we are to calculate the period of the girl's swing. So what we need to first know is understand, okay, how the oscillation occurs. So for period, that would actually be one full oscillation. And looking at that and what the question is saying from her original rest position to the first maximum point, this 1.17 seconds is actually the movement from the rest position to this maximum point. So given that this is 1.17 seconds, the full period would therefore be 1.17, another 1.17, a third one, and a final one for her to return back to her original state of motion. Not just back to the original position, but also back to original position and state of motion. So our answer would therefore be 4 times of 1.17 seconds, which is 4.68. Now for part B, the instrument used to obtain the measurement, straightforward, it should be a stopwatch. And the error associated with calculating the period and a way to reduce this error. So a possible error would be due to the human reaction time. And a way to overcome or at least reduce the error is to either measure 10 periods and divide by 10, or to take multiple readings and take the average. So when you do your practicals, you actually take a combination of both. So what we usually do during practicals when we are asked to find the period of a pendulum would be to measure 10 periods divided by 10, and then we do this 3 times in total. So we don't just measure 10 periods, we measure 10 periods 3 times in order to get a much more accurate and precise reading. Moving on to question 2, we have a cube with a length of 2.24 centimeters and a mass of 170 grams lying on one of the sides on the ground. So we want to calculate the density. So going back to the formula for density, which we went through in the MCQs, what we have is rho equals to m over v. And because we want SI units, we have to convert all the measurements, okay, from whatever units here into SI units. So 170 grams is 0.170 kilograms. 2.42 centimeters is 0.0242 meters. Remembering to cube it. It is very important that we maintain the brackets so that we do not accidentally cube it first and then divide by 100, for example. So putting this into the calculator, we get our answer here, and we then convert it or round it off to 3 significant figures to get 12,000 kg per meter cube. So for part B, we want to calculate the pressure. So for pressure, okay, we need to remember that it's given by force over area, and the force that the cube exerts on the ground would also very clearly be its weight. So I've just straight away substituted for mg, and the area would still be the same length but squared instead of cube this time. So again, doing the math and going through the steps, we get 2,903 newtons per square meters, which we know that is the SI unit pascals. So 3SF gives us 2,900 as our answer. So just as a way to go through, how do we actually award the marks? So for example, if you're calculating the density, 1 mark would be appropriate substitution. We are seeing that you are using the correct formula and the correct values, and another mark for the answers. Why this is 3 marks? You get 1 mark for identifying that the weight is actually the force here. Another mark for the correct values substituted into the formula, and the correct mark here for the final answer of 2,900 pascals. Question 3. A parachutist of mass 70 kilograms jumps out of a plane, and we've got a speed time graph. So the question asks for you to draw the free body diagram at t equals to 0. So at t equals to 0, okay, is just as the parachutist jumps out. So because that is the point where the parachutist just jumps out, we do not draw any air resistance because there is no speed. So when you're not traveling through the air, there's no resistive force. Similar like friction. When something isn't moving, we don't experience as much friction. So over here, we don't have any air resistance. So answer would be just a simple downward arrow labeled very clearly as the weight. We accept both the symbol W or if you write out weight in full. Moving on to the remainder of the question, explain why the acceleration of parachute decreases at time equals to 50 seconds. So if you see here, we've got 2 marks. There therefore needs to be 2 very clear points. And our 2 points are that as the parachutist's speed increases, the air resistance increases while the rate remains the same. Very simple answer, but the distinction has to be made between the speed and the acceleration. Someone can still be increasing in speed but decreasing in acceleration. If we go back to the graph, you will notice that his speed is still increasing, but the gradient is getting shallower because over here, okay, the acceleration is decreasing. And the reason for that is because the air resistance is increasing, so the resultant force is decreasing over time, which then causes the acceleration to decrease. So our second point over here would be that the resultant force decreases. It would be helpful as well, but not necessary, for you to state the law that accounts for this. And in this case, this would be Newton's second law, which tells us that F equals to ma. For B part 2, explain why the speed of the parachutist is constant at time equals 200 seconds. We have to remember the stem of the question asks us by considering the forces. So at 200 seconds, the speed is constant, and that is because of a concept we went through during the MCQs, terminal velocity. The the force of air resistance experienced is equal to that of the weight that the parachutist experiences. So the resultant force is 0, so there's no acceleration. And you can also state that this is an explanation or an application of Newton's first law. Part C, the speed of the parachutist decreases at 300 seconds, and suggests a reason for this and explain why this results. So that is because the parachute was opened. So as the parachute is open, you have a larger surface area now falling through the air, which increases the air resistance to be greater than weight. So what happens now is, if you draw a free body diagram, you've got air resistance pointing upwards, and this force will be greater than the weight acting downwards. So the resultant force will be upwards. And since the parachutist is falling with a velocity downwards, this upwards acceleration would cause a decrease in speed. Or you can also say that it was a deceleration because the acceleration and the velocity are pointing in opposite directions. Question 4. So what we have is a box P and a box Q of 8 and 4 kilograms, and you're pushing box P with a constant force F. So they are both moving together with an acceleration of 0.25 meters per second squared, and the resistive forces acting on both boxes is 10 newtons. So we want to calculate force F on box P, and how we do that is using Newton's second law. So that would be F equals to 10 F minus 10 equals to ma. Apologies for this. This should be Newton's second law and not first law. Why F minus 10 newtons? Because there is 10 newtons of resistive force, so that will be pointing in the other direction. And ma, okay, would just be the combined mass of the system and the combined acceleration of the system. So that gives us 3 newtons. So that tells us that F equals to 13 newtons by Newton's second law. Not the first law over here, but actually the second law. So moving to part B, we've got now 2 boxes placed on a smooth surface and pushed with the same force F. So very important to see the smooth surface. This is a mistake that students would make, and I believe I also made that mistake when I was going through this in class, so please take note. So now when there's a smooth surface, there is no longer any friction, and we want to calculate the force of box Q acting on box P. So if we draw the free body diagram of box Q, this is the box that's being pushed, okay, and there's a force of P acting on Q. Of course, you want the force of box Q acting on P, but we will get to that. And again, sorry, Newton's second law, F equals to ma, tells us that the acceleration of the two boxes of the whole system is 1.083 meters per second squared. Now we know that FPQ is equals to the mass of box Q times the acceleration here, which gives us 4.33 newtons. Okay, once we round it off. And we know that box Q acting on box P by Newton's third law must be the same force, just opposite in direction. So therefore our answer is 4.33 newtons. Now question 5, I've got a uniform plank hinged at one end. Okay, so this end over here, it has a length of 2 meters, a mass of 3 kilograms, and then there's a mass of 10 kilograms placed here and a string tied here. So part A, the principle of moments, okay, this is just for pure memory work. For an object in rotational equilibrium, the sum of clockwise moments about a pivot is equal to the sum of anti-clockwise moments about the same pivot. Now draw and label the plank, the weights. So right from the center of gravity over here, you have the weight W, and it would also be good for you to label this as 1 meter because the center of gravity is 1 meter from either end. So now moving on, I've just preserved this diagram here. We want to calculate the force in the string to keep the plank horizontal. So first we know that this is the pivot. So let's consider the principle of moments using this as the pivot. So we've got the sum of clockwise moments about this point x here equals to the sum of anti-clockwise moments about the same pivot x. And we know the formula for moments is force times perpendicular distance. I am not going to go through the maths itself, but what we have is our clockwise moments. The weight over here is 100 newtons. Sorry, weight over here is 100 newtons of 10 kilogram mass, so that's downwards, providing a clockwise moment, 0.6 meters from the pivot, and then the weight of the plank, 30 newtons, 1 meter away, and whatever string, okay, force here, the force exerted by the string is upwards, which would be anti-clockwise, 1.8 meters away from the pivot. So when you do the maths, you would find that the force is 50 newtons. So in part D, how can we reduce the force in the string to keep the plank horizontal? So there are two potential ways of doing so, both either by one is by reducing the clockwise moments, the other is by keeping the moments but changing how this equation looks like. So the first is to tie the string further away, because even if you have the same moment, if the distance is larger, so instead of 1.8, let's tie it at 2 meters, then you would have a smaller force required. The other way is to reduce this. If we move the 10 kilogram mass closer to the pivot, so we change this to say 0.3 meters away, then the left hand side of the equation will decrease and you do not need such a large force to get rotational equilibrium by balancing the clockwise and the anti-clockwise moments. So now moving on to question 6, the distance time graph of a crate of 6 kilograms that's being pushed up a slope. So you can see over here its distance is increasing and then it is stationary afterwards. So state the total distance. Since it's state, no calculations are required. You can see that it has only moved 40 meters. Next, calculate the speed of the crate at 5 seconds. So t equals to 5. Now we need to know the formula or the definition that the speed is the gradient of the distance time graph. And this actually can be given by delta D over delta T. So if we look at this triangle over here, the change in distance divided by the change in time. So the change in distance would be 40 meters, and the change in time, or the time taken, would be 6 seconds. We round it off to 3SF to get 6.67 meters per second. The energy in the kinetic store will be given by the formula half mv squared, and then we substitute 6 kilograms and 6.667. Notice I've used more significant figures here in my intermediate steps because I would like to reduce the errors that are caused by rounding. Okay, so in your intermediate steps, try as much as possible to use one more SF or even two more SFs that is actually absolutely required in your answers, so that rounding errors do not accumulate, and we get over here 133.33 joules, which we finally then round off to 3 SF in the final answer. Question 7a. So this is purely memory work, and I will just let you pause this, okay, before we move on to 7b if you need some time. So for 7b, explain why liquids have fixed volumes but are able to flow. So this is because even though we have very strong forces of attraction between the particles that cause them to remain closely packed and unable to be compressed, they're not strong enough to be fixed in their positions. So this means that the particles, they're able to slide past each other, and the liquid can flow and change its shape because the particles are able to move. The shape of the liquid is not fixed, therefore, okay, the liquid can flow while keeping its fixed volume. So question 8, you see a water wave here, particle P lying on the wave here, and state the direction of the particle P at the next instance. So a trick to finding out how the particles move, okay, is to actually draw, at least in pencil if it's possible, the wave moving slightly in the direction that it's stated. So you see over here the water wave moved to the right. So this is how the water wave would look like just a tiny instant afterwards. And you can see that point P, as we know, the water wave is a transverse wave, would oscillate in a perpendicular direction to the motion of the wave. So that means that point P actually oscillates up and down, and you can see that in the next movement, it would have gone upwards, so the direction would therefore be upwards. I'm transferring the diagram here and calculate the frequency of the wave. So over here we see 9 meters being measured, but be very careful about what actually is the wavelength. Notice that I've colored it, okay, red and blue, just to make it very, very clear that one wavelength is one cycle like this. So knowing that one wavelength is 6 meters, and using our formula for wave speed, v equals to f lambda, and substituting it, we get that the frequency is 2 hertz. So what this means is that the oscillations occur twice every second. So every second, 2 complete oscillations occur, 2 periods occur. And using that, t equals to 1 over f, that tells us that the period is half a second. Because it only takes half a second for the period, 2 of them can fit into 1 second, and your frequency is therefore 2 hertz. So knowing that the period is half a second, and that p starts off here at the middle equilibrium point, how do we describe the motion of particle p over the next 0.75 seconds? So well, first, we need to realize that 0.75 seconds can be broken down into one period, 0.5, and a remaining 0.25 half period. So from 0 to 0.5 seconds, one complete oscillation occurs. So we said just now it moves up, right? So it moves up to the maximum displacement, down to the minimum displacement, back to the equilibrium position. One oscillation complete. Then from 0.5 to 0.75, there's only half a period, so half an oscillation occurs. It moves up to the maximum displacement and then back down to the equilibrium position. and then that's the 0.75 seconds over. Of course, after 0.75 seconds, it would continue in its oscillation, okay, back and forth. But we only needed to describe 1.5 periods. Now, question 9, we've got a water heater with a lid and a smooth white plastic exterior, and state the method of heat transfer from the heating element to the water. So that would be conduction, because the heating element is in contact with the water, and the particles in the heating element vibrate vigorously and collide with the neighboring water particles, thereby transferring energy in the internal kinetic store and heating the water itself. I'm going to keep the diagram here for part B. Describe how the water in the tank gets heated up and to draw to better illustrate your answer. So this is convection, and we need 3 points to talk about convection. Based on the earlier answer where the water got heated by the heating element via conduction, okay, what happens now is after it heats up, it expands to become less dense and it would rise. So that's your first point. Second point, the cooler, denser water sinks to take its place. Okay, I've illustrated in red and blue just to make it clear that is not required. Please do not write in your exam paper using red pen. But the cooler, denser water sinking to take its place is the second part, the second mark required. And then this cycle repeats because now the water takes its place, it can get heated up by conduction, and so on and so forth. The cycle will repeat and set up a convection current, that being self-repeating. This is your third point. So in the next part, what would happen should the heating element be placed near the top of the water heater? We just explained by saying that the water below the heating element would remain cool, as the warmer, less dense water would not be able to transfer heat via convection. It cannot sink because it is already less dense. And water is a poor conductor of heat. So it would generally not be able to transfer heat very well to the water under the heating element. Now, refer to the diagram and state and describe how heat loss is reduced. So first, the lid traps air and reduces heat loss through convection currents with the surrounding air. So any air that from conduction gets heated up by the warm water at the surface would be trapped within. It would not lose a lot of that heat to the surrounding air by escaping. Okay, next, the container is plastic, is smooth and white, so making it a poor emitter of radiation. And because it's also plastic, a poor conductor of heat, that reduces heat loss by conduction. Now let's move on to question 10. So question 10, a cyclist travels from point A to B to C. He doesn't stop through the journey, and you have a speed time graph here. So part A asks to describe the motion of the cyclist from A to C. So keeping this in mind, okay, what it looks like, how do we describe the motion of the cyclist? We can say that the cyclist accelerates uniformly from A to B and travels at a constant speed from B to C. As we saw just now, okay, it was a straight line and after that a horizontal line. So next, to calculate the acceleration, we must first find that the acceleration is the gradient of the speed time graph. So delta V over delta T, change in velocity over the time taken. Now, some of you might have made the mistake, not read the graph very well, and went and divided by 5. But if you had noticed, the units of the graph were in minutes and not in seconds. So that might have tripped you up, okay, and you would have gotten something like 1.6 meters per second squared. However, okay, what we have is actually 300 seconds instead of 5 seconds because it's in minutes, giving an answer of 0.0267 meters per second squared. Next, calculate the distance traveled by the cyclist. We need to remember that the distance traveled is the area under the speed time graph. So again, if you made that mistake of assuming that the units were in seconds, you would have gotten the wrong answer here. But using 300 seconds and calculating the area under the graph of this trapezium by breaking it up into a triangle over here and a rectangle over here will result in 3,600 meters or 3.6 kilometers traveled from point A to point C. Now looking at D, okay, we want to state the displacement and the velocity of the cyclist. Sorry, we want to complete the figure first from point C back to point A at constant deceleration. So first, we want to know that the distance is the area under the speed time graph, and constant deceleration is a straight line. So that will be a triangle to wherever it is. So this tells us that this area here would be the same as the area of whatever triangle is, so 3,600 meters. And when you do the maths, you find that that is 900 seconds or 15 minutes. So back to point A is 15 minutes after he has reached point C and has started going back. Then, because he has gone back to point A, the displacement would be 0 meters, because displacement is the total distance between the starting point and the ending point, which here is 0, and velocity is the displacement over time. And if the displacement is 0, there's therefore no velocity. Moving on to a final question, question 11. There's a gun and placed directly in front of a block and shot with a bullet of 25 grams with a certain velocity. So explain the principle of conservation of energy. You see over here, energy cannot be created or destroyed. It can be transferred from one store to another store, and the total energy of an isolated system is constant. Calculate the speed of the bullet. So we started off with 1,500 kilometers per hour. So that's 1,500 kilometers divided by 1 hour. Converting this into SI units, that would be 1.5 million meters and 3,600 seconds, which gives us 417 meters per second in 3SF and SI units. Energy in the kinetic store, we already had a question earlier about this. So the formula is given here. We just need to make sure we try and use the intermediate values. Instead of 417, we use 416.67 over here. This rounds off finally to 2170 joules in 3SF. Next, the bullet borrows a distance of 20 centimeters, which then together move at 22 meters per second. So calculate the average frictional force. So this is a longer question with more steps. So we first start off by calculating the total kinetic energy in the system. And that is done by taking the total mass and the new velocity and putting it into our equation half mv squared to get our final energy in the kinetic store after the collision. By the principle of conservation of energy, the work done by friction, okay, is the difference in the energies. We started off with 2170.1 joules in the kinetic store of the bullet and 0 in the block. In the end, we had 732.05. So that difference here must have gone somewhere. And remember, transfer of energy being work means that friction must have transferred the energy somewhere. So this 1438.05 joules transferred somewhere is the work done by friction. Finally, we use work done being force times distance, and we get that friction is 7,190 newtons when we round off to 3 significant figures. So remember that 20 centimeters is not SI units. We do need to convert to 0.20 meters in order to find the magnitude of friction here. Finally, just to finish off the paper, describing the energy transfers, we see that some energy in the kinetic store of the bullet was transferred to that of the block, like we said earlier, and that caused it to move. Some other energy was transferred from the systems to the surroundings mechanically. This would be sound or friction, causing this transfer to the surroundings. Okay, so we've come to the end of the paper. So please take note that for the later section, questions 10 and 11, these questions are two questions where you have to pick one. So if you do both questions, we would only mark the first question, which in this paper would have been question 10. So please read your instructions very carefully in order to make sure you don't waste time doing unnecessary questions that would not be marked. And if you've attempted a question but decided you prefer to attempt the other, please make it very clear by either writing a note or by cancelling out your answers so that the markers know that you are asking them to ignore one question and to mark the other question, but only for the final section. In the earlier section, in this case questions 1 through 9, there are no optional questions. All questions should be done. So at the end of the video, okay, we've come to the end of this paper. Please take the time to rewatch sections to understand any of the explanations for questions you might struggle with a little bit more, or if it was a little bit too fast for you and you just need to slow it down, please also feel free to do so by playing the video at a slower speed as well.